India's Chandrayaan-3 moon mission has already proven historic. It put India in the history books for being the fourth nation to ever successfully land a spacecraft on the moon, and the very first to ever land at its south pole. The lander Vikram and rover Pragyan already made discoveries that could profoundly impact our understanding of the moon's chemical composition and geological history, and has given the world vital data that will aid future return missions to our lunar neighbor. And yet, for all the praise, which is well-deserved, it's what Chandrayaan-3 did not discover, but should have, that I find the most intriguing. Have you noticed it too? India's NASA equivalent, ISRO, the Indian Space Research Organization, made press releases before the launch. And there was always one thing they claimed they were primarily there to find. One reason, the South Pole was picked out over all other locations. One mystery about the moon that is deepening. The more we investigate, and yet needs to be solved, before we can expect to start setting up permanent bases up there. Simply put, where is all the water? It was India's Chandrayaan-1 mission that helped provide some of the clearest proof that the moon's polar craters might hold water ice. Water on the moon had been hypothesized since the 1960s, and in 1971, Apollo 14 found some traces of water vapor at the lunar surface. But water ice itself proved difficult to pin down. Scientists thought that if water ice was anywhere, it would be in the craters at the north and south lunar poles. These craters were angled such that they never received direct sunlight, and thus were very cold, some of the coldest places in our entire solar system. The perfect forming ground for ice. Sadly, images of these crater cold traps were too low resolution, or simply too dark for us to know for sure, and while there were numerous detections of hydrogen on the moon's surface, it was unclear whether this took the form of actual water ice or not. However, in 2009, signs of hydration began to emerge. Chandrayaan-1, carrying a NASA moon mineralogy mapper, found the first definitive spectroscopic signatures of water ice in dozens of craters congregated around the moon's poles. This water map was later confirmed by Chandrayaan-2, leaving scientists increasingly confident that there was potentially 600 million metric tons of water ice to be found in the moon's darkened craters. Water on the moon is a big deal. More and more nations have goals of setting up bases on the moon, and being able to source your water from the moon's surface saves you from having to spend huge amounts of resources getting it up there. Water is vital for human life, but also could be broken down for hydrogen and oxygen, useful ingredients for rocket fuel, or a breathable atmosphere in your moon base. So it should come as no surprise that when Chandrayaan-3 began to make its way towards the moon, one of the things the media reported it was hoping to find was water ice. Chandrayaan-3 was launched on the 14th of July, 2023. It was made up of a lander module called Vikram, a small rover called Pragyan, and an orbiter module that carried the other two components across the gulf of space. On the 23rd of August, Vikram, with little Pragyan tucked inside, touched down on the moon's surface at the beginning of a lunar day. But time was not on their side. Chandrayaan-3 was a surprisingly cost-effective mission. While NASA's Artemis mission launches will each cost on average $4.1 billion, the entire Chandrayaan-3 mission only came to 6.15 billion rupees, or about $75 million. Ironically, less than what many modern blockbuster space films take to produce. Perhaps Hollywood should consider filming their next moon film on site. However, With this lower budget came technological limitations. When the lunar night fell, Vikram and Pragyan would be subjected to temperatures of -120 degrees Celsius, temperatures they were not designed to survive. A lunar day lasts 14 Earth days. The Chandrayaan-3 mission would need to complete its major objectives in that time, as their odds of surviving to the day after that was slim. And so, Vikram lowered its ramp, and Pragyan the rover powered up and headed out down onto the moon's surface. Pragyan is a 27-kilogram, six-wheeled rover that came equipped with an alpha particle X-ray spectrometer, APXS, for analyzing the chemical composition of the moon by firing radiation at it and seeing what wavelengths bounced back, and a laser-induced breakdown spectroscopy instrument that does a similar thing, but this time by firing a laser at the target of interest and analyzing the light wavelengths that are released by the resulting plasma. These two tools together would be enough for Pragyan to attempt to find water or any other interesting substances, confirming their composition for scientists once and for all. And so, it set to work deploying both instruments on the ground next to it. Within days, the results started coming in. Aluminium, calcium, iron, chromium and titanium were all found on the moon's surface, along with other interesting elements like oxygen. Indian scientists were most excited at the first ever in situ measurement of sulfur at the moon's pole. Sulfur is an exciting element to find, as it helps us understand the evolution of the moon over time and indicates there used to be volcanic activity in the region. But in spite of all these discoveries, there was one element that was not showing up in the analysis. The all-important hydrogen was notably absent. Pragyan set off to explore further afield. Guiding the rover was all done manually by scientists back on Earth, looking through Pragyan's onboard navigation camera. This had to be carefully done, as the signal delay between Earth and the moon meant that orders for the rover to halt lagged by a little under 3 seconds, time that might make all the difference if the little six-wheeled rover was to avoid overturning. And indeed, this nearly happened. Early on in Pragyan's journey, the rover had to speedily stop to avoid falling into a large 4-meter crater scientists hadn't initially realized was there. I say speedily. Pragyan's move speed was 1 centimeter per second, hardly the fastest of sprinters. Over the course of its 2-week life, Pragyan traveled no more than 100 meters from Vikram. Fortunately, the crater was detected in time, and the scientists were able to turn around and choose another route. However, when you look at Pragyan's route, you notice that there was a second moment where Pragyan did not travel down into a crater it came across, instead electing to go around. No photos of this second crater are currently available, so we are left to conclude that no ice was spotted there. Vikram itself did not remain idle during this time. It performed temperature readings of the moon's surface, digging 10 centimeters deep to measure the moon's warmth at different depths. It measured the plasma content of the atmosphere. Good news, there's not much up there, so radio communication to the moon likely won't get much interference. It detected a possible moonquake, which, given the small 2-week window, was some excellent timing. At the very end of its journey, in a moment of final enthusiasm, the Vikram lander even successfully performed a 40-centimeter-high hop, firing its boosters to lift itself off the ground, moving 30 to 40 centimeters along from its previous destination. Indian scientists had wanted to test how easy it would be for future landers to one day propel themselves back into orbit from the moon, and this was a useful practice run. But none of this helped the Chandrayaan-3 mission to find water ice. By the 4th of September, time was up. Vikram and Pragyan were both ordered to power down. ISRO scientists had hoped to be able to wake them up again once the night ended. But this hope proved to be fruitless. The two lunar explorers had communicated with the Earth for the last time. ISRO and the scientific community at large lauded their efforts and called the mission a success. And indeed it was, as India had gained first-hand data from the moon that would be extremely helpful in building a picture of conditions at its poles, along with furthering our understanding of the moon's history. However, it definitely raises a mystery. When I first heard that water ice had been detected on the moon, I envisioned in my mind frozen ice lakes or possibly tall penitents. Perhaps a light frost, as vapor from the moon's atmosphere ended up trapped in these darkened craters, freezing over the surface and building up over time. We know from orbiters like Chandrayaan-1 that water ice is indeed in these craters. And yet, Chandrayaan-3 has joined other missions in failing to actually see this ice for themselves. I remember feeling similarly disappointed when I first saw the images captured by ShadowCam, a NASA camera carried on the South Korean Danuri moon orbiter. ShadowCam was so good at detecting light, it could see into the polar craters that hadn't seen direct sunlight in millions of years without issue. And yet, once again, there was nothing there, nothing but arid dust. Given that Pragyan's analysis of the lunar regolith revealed no signs of water molecules, where is the water ice that Chandrayaan-1 detected? While this mystery is confusing, Chandrayaan-3 offers us a possible answer. Not through Pragyan's explorations. It's actually Vikram that possibly hinted at the solution. When Vikram used its Shasti temperature sensor, it was able to take 10 different readings of the moon's temperature, starting at the surface and working its way down in 1 centimeter increments. What it found in the space above the moon's surface was a temperature a little under 60 degrees Celsius, definitely too hot for you to walk around in, if you happened to be on the moon and somehow didn't care about the lack of air. But curiously, as Shasti measured deeper and deeper beneath the surface, this sweltering temperature dropped off fast. By 8 centimeters deep, the new temperature Vikram was detecting was minus 10 degrees Celsius. That's a big drop. From this, we see that lunar regolith is a really poor heat conductor. But that also indicates quite clearly that the best place we're likely to see ice is not resting on the moon's surface, but we actually need to look beneath it. There's much we don't understand about the moon and its water cycles. There's growing evidence that the moon contains quite a lot of water, and yet extracting it will take understanding where that water can be found and how it moves throughout the long lunar days and nights. Is it affected by solar radiation? Is it trapped in hidden deposits? Although Chandrayaan-3 only lasted 2 weeks, which I'm sure is less time than ISRO scientists would have liked, it has offered us vital insights into conditions on the moon. As far as water is concerned, at the very least, it has given future astronauts this one piece of advice. If you want to find a drink of water on the moon, you might want to start by bringing a shovel. Recent studies suggest the moon's water may exist in unexpected forms, not as sheets of surface ice, but potentially bound within mineral structures or trapped in microscopic gaps between lunar soil particles. Scientists now theorize that solar wind could be continuously delivering hydrogen atoms to the moon's surface, where they combine with oxygen in the soil to form hydroxyl molecules and trace amounts of water. This process might create a sort of water cycle, where molecules migrate toward colder polar regions during the lunar night, only to be broken apart by sunlight during the day. The upcoming NASA Viper rover mission, scheduled for launch in late 2024, aims to solve this mystery by directly sampling lunar soil at the South Pole. Equipped with a 1-meter drill, Viper will search for water ice beneath the surface, where Vikram's temperature readings suggest it might be stable. Meanwhile, China's Chang'e 7 mission, planned for 2026, will carry a water molecule analyzer and drilling equipment to conduct similar investigations. These missions may reveal whether the moon's water exists in accessible concentrations or is too widely dispersed to be useful. New analysis of Chandrayaan-3's data reveals another intriguing possibility. The water detected by orbital instruments might not be pure ice at all, but rather a sort of dirty ice mixed with lunar soil. Laboratory experiments show that when simulated, lunar soil is exposed to water vapor in vacuum conditions, the water molecules become tightly bound to soil particles, rather than forming visible ice crystals. This could explain why surface rovers see only dry regolith, while orbiters detect hydrogen signatures. The search for lunar water has taken on new urgency, with multiple nations planning permanent bases. Recent discoveries suggest water molecules might be more mobile than previously thought, possibly migrating through the lunar soil over time. Some scientists propose that cold traps at the poles could contain layered deposits of ice and dust built up over billions of years, a potential time capsule of the moon's history. Future missions may need to drill several meters down to reach these ancient reservoirs, if they exist. Advanced spectroscopic techniques now being developed could help distinguish between different forms of lunar water, whether it's chemically bound in minerals trapped between soil grains or exists as subsurface ice. The European Space Agency's Prospect payload, destined for a future Russian lander, will use heating experiments to release and analyze any water from drilled samples. These new approaches may finally solve the puzzle that Chandrayaan-3 helped bring into focus. The moon clearly contains water, but unlocking its secrets will require digging deeper, both literally and scientifically. Emerging technologies like neutron spectrometers and ground-penetrating radar could map subsurface water deposits from orbit with unprecedented precision. Private companies are also joining the hunt. Intuitive Machines plans to deploy a drill on its 2024 moon mission, while ISpace aims to test water extraction technologies. The race to characterize and potentially utilize lunar water has become one of the most exciting frontiers in space exploration, building on the foundation laid by missions like Chandrayaan-3. Recent computer modeling suggests another fascinating possibility. The moon's water might be unevenly distributed in micro-cold traps, tiny shaded areas that could contain more water than the large craters. These could be as small as pebbles casting shadows, creating millions of microscopic storage spots across the lunar surface. This would explain why previous missions have struggled to find concentrated ice deposits, while orbital data indicates widespread hydrogen. Future exploration strategies may need to account for this potential hidden water network scattered across the moon. The next generation of lunar landers will carry more sophisticated instruments to investigate these possibilities. NASA's Artemis program intends to deploy surface experiments that can monitor water molecules moving through the lunar environment over extended periods. Meanwhile, new analysis techniques applied to existing data from Chandrayaan-3 and other missions continue to reveal subtle clues about the Moon's water cycle. Each mission brings us closer to solving this cosmic mystery, with implications that could transform humanity's future in space. Cutting-edge research now suggests that lunar water might not be a static resource, but part of a dynamic system influenced by meteorite impacts, solar activity, and even the Moon's own seismic tremors. Some scientists propose that these processes could periodically expose or redistribute subsurface ice deposits. Understanding this complex interplay will be crucial for future lunar settlements hoping to utilize local water resources. The discoveries made by Chandrayaan-3, though not definitive, have opened new avenues of investigation that are reshaping our understanding of Earth's closest celestial neighbor. Exciting new research from the Lunar and Planetary Institute suggests that the Moon's water may be far more dynamic than previously imagined. Their latest models indicate that water molecules could be constantly hopping across the lunar surface, moving from warmer to colder areas with each 14-day lunar cycle. This phenomenon, called thermal pumping, might explain why surface missions struggle to detect water while orbital instruments keep finding hydrogen signatures. The molecules may be in constant motion just below the detection threshold of surface instruments. Breakthrough technology in miniaturized mass spectrometers could revolutionize the search. NASA's upcoming Lunar Trailblazer orbiter, launching in 2024, will carry an advanced imaging spectrometer that can map water signatures at unprecedented resolution, detecting variations at scales smaller than a football field. Meanwhile, the German Aerospace Center has developed a new laser spectrometer that can detect single water molecules in soil samples, technology that may fly on future European lunar missions. Recent analysis of meteorite samples suggests an intriguing possibility. The Moon's water might be partly homegrown. Certain lunar minerals show evidence of containing indigenous water that was present during the Moon's formation, challenging the long-held assumption that all lunar water was delivered later by comets or solar wind. This could mean water is more deeply integrated into the Moon's geology than we thought, potentially existing in mantle rocks that were brought to the surface by ancient volcanic activity. The private sector is bringing innovative approaches to lunar water exploration. Astrobotic's upcoming Mission 2 will test a novel heating and sniffing technique, using a robotic arm to scoop soil, heat it in an enclosed chamber, and analyze the released gases. Another company, Lunar Outpost, is developing mobile water prospecting rovers that could survey large areas autonomously. These commercial efforts complement government missions, creating a multifaceted approach to solving the lunar water puzzle. Scientists are now investigating whether the Moon's water could be chemically locked in unexpected forms. New laboratory experiments show that under lunar conditions, water can react with metallic iron in the soil to form iron hydroxides, compounds that don't show up in traditional water detection methods but could release water when heated. This hidden reservoir might account for some of the discrepancy between orbital detections and surface observations. The latest thermal models of permanently shadowed regions reveal another surprise. These areas might experience brief periods of indirect heating when sunlight reflects off nearby crater walls. These thermal spikes could cause surface ice to sublimate and redeposit in slightly different locations, creating a complex, ever-changing distribution pattern. Future missions may need to time their sampling carefully to catch these volatile compounds in stable conditions. Advanced machine learning techniques are now being applied to decades of lunar data, uncovering subtle patterns that hint at water movement. One intriguing finding suggests that water signatures appear to shift slightly between lunar morning and afternoon, possible evidence of a diurnal cycle we're only beginning to understand. As analytical tools grow more sophisticated, we may discover that the moon's water behaves more like Earth's atmospheric moisture than the static ice deposits we initially imagined. The next frontier in lunar water research involves studying how water interacts with the moon's unique soil properties. Recent experiments with simulated lunar regolith show that electrostatic forces can cause dust particles to trap water molecules with surprising efficiency. This electrostatic sequestration might create invisible water reservoirs clinging to dust grains, explaining why our current detection methods struggle to find it. Solving this mystery could require developing entirely new exploration techniques tailored to the moon's alien environment. As international interest in lunar resources grows, new collaborative efforts are emerging. The International Lunar Research Station, planned by China and Russia, and NASA's Artemis Accords partners, are all prioritizing water research. This global focus ensures that multiple approaches and technologies will be brought to bear on the problem, increasing our chances of finally understanding the moon's most elusive resource. The answers may come from anywhere: a sudden breakthrough in data analysis, an unexpected finding from a new instrument, or perhaps that crucial shovel of soil that finally reveals the moon's watery secrets.